Hello, my name is George Turbifil, and my research revolved around an article published by NASA detailing the events that took place at the Larsen C ice shelf on July 10th in Antarctica. It was first reported by Project METIS, an Antarctic research group in the UK. The rifting has actually been present for decades, but with a recent growth in 2014. For 2 straight days, enormous rifting and cracking of the ice shelf caused an iceberg named Nansen, which larger than the size of Delaware, to break apart from the ice shelf. It covers 2,240 square miles and weighs approximately a trillion tons. The Larsen C ice shelf is located on the east side of the Antarctic Peninsula. It is the fourth largest ice shelf within Antarctica's geographical area, and itself lost 10% of its area as a result of Nansen leaving. Now, there are some common misconceptions about this event when it first went public. Numerous people thought that the whole Larsen C ice shelf itself broke off and floated into the South Ocean. That is untrue. Only a portion of it, named the Nansen iceberg, broke away due to the rifting. Approximately 90% of Larsen C's area is still intact. It is necessary to distinguish between an ice shelf and an ice sheet. Ice shelves are frozen waters floating on top of the ocean, neighboring the ice sheets, whereas ice sheets, which are mostly Antarctica's glaciers. Not all ice shelf rifting and separations are abnormal or are a result of anthropogenic actions. If in balance, ice introduced by snow equals the ice lost through iceberg calving and melting. Ice lost through sea ice and iceberg melting, irregardless of the size for the most part, is normal if the system is still in balance. However, if the system is not in balance, meaning that there is less ice gain when compared to ice loss, the system is instead destabilized. For example, in 2002, icebergs separating from the Larsen B ice shelf was a result of a destabilized system. The more the rifting, the separation, and melting, the more the ice sheets are in direct contact with the tides, and thus the more ice lost. The cryosphere plays a critical role in the stability of the global climate. The thermohaline conveyor belt discussed in Lab 6 is responsible for bringing nutrient-rich cold upwellings to the surface near multiple continents. Many migratory oceanic life and local economies depend on this upwelling. The Antarctic bottom water section of the belt are very cold and very saline, causing them to sink rapidly. If more ice continues to be calved and melted, this will increase the temperature of the water and decrease the salinity of the surface waters, thus decreasing this density and ultimately affecting both the sea surface currents and the thermohaline conveyor belt. Any change in the direction, speed, or frequency of the belt can cause a dramatic effect felt through the food chain. This increase in water temperature also has effects on the concentration of greenhouse gases in the atmosphere. The solubility of carbon dioxide in the ocean is directly related to the temperature of the water. Increases in ocean temperature decreases the solubility. Thus, this will reduce the CO2 in the ocean and increase in the atmosphere, increasing the greenhouse effect, which will increase global temperatures. These higher global temperatures also have an effect on the ocean temperatures, thus creating a positive feedback loop.